Okay, so continuing with a discussion of boundary value problems, and in particular the shooting method. First, a very quick recap from last time. This is the problem we're solving, second order ODE on a bounded interval, AB, with solutions specified at the endpoints. These are boundary conditions. Um, and the first approach that we've looked at for solving this problem is the shooting method. So what the shooting method does is treat this boundary value problem as an initial value problem with these initial conditions where we have to guess at the right value of t, the slope, so that we will satisfy the other boundary condition at x equals b. Um, so to solve such a um, initial value problem that's based on a second order ODE, we rewrite it as a first order system of ODEs. Um, and then we make a guess at t and solve a problem using whatever numerical method, like a time-stepping methods from chapter 12. And what we're basically doing is solving this equation. We want to find a root of this function, um, f of t, where y of y1 of x semicolon t, that is the solution that we get by choosing t for this initial condition. We evaluate that solution at x equals b, and we check if it satisfies beta, because beta is what the solution is supposed to be equal to at x equals b. Well, after only a minute, the recording already cut out. So, so basically, we're trying to find the value of t that satisfies this equation. So it's a root finding problem. Now, in the case of a linear equation, I'm not sure what new page for some reason where it's not needed. Let me put all that back onto one page. Okay. Linear problem that has this form. That's what was covered last time. All we have to do is solve these two. Well, that time I recorded for a whole 36 seconds before it cut out. So in that case, finding a value of t it's a homework problem, but it only takes a little bit of work to do once you have those solutions. Today the focus is on nonlinear problems, and I'll start that on a new page. Um, so what do we do in that case for a BVP converted into a to first a that's of first order ODEs as an IVP. So the same problem that I laid out last time, because I feel like that causes problems for recording otherwise. So it's still um, all of this is still what we're solving. Um, so so what we do is now we're trying to find a root of this function using whatever root finding method we can, because now it is a nonlinear equation. Okay. Um, let's use some root finding method, like a new secant uh, method. The root of this function, f of t, equals y1 of b with parameter t minus beta. So for Newton's method, we need of a derivative of this function, f prime of t. So that would be equal to partial derivative of y1 of b of t, and then beta is a constant, so that doesn't make any contribution. Okay, so because as you know from chapter 10, Newton's method requires a derivative. So how do we get the derivative of a solution of our uh, ODE, our system of ODEs? Um, well, what we can do is um, take a derivative of the equations that y1 satisfies with respect to t. So what we have is, and I'll just, instead of scrolling again, I'll just repeat the system of ODEs that we have. So y1 prime is equal to y2, and then y2 prime is equal to f of x, y1, y2. Remember from last time, these 1s and 2 superscripts are not exponents. They're not squaring or raising anything to first power. So don't even go there. Now, keep in mind, when I have prime here, prime refers to derivative with respect to x. Any derivative I have with respect to t, I'll use the partial symbol here. So I will let z1 equal the derivative of y1 with respect to t. So I'll use that notation also, subscript, the usual notation for partial derivatives. And z2 is the derivative with respect to t of y2. So it's this derivative that we need. We need to evaluate z1 at x equals b to get this derivative of capital F. So what I could do is figure out, okay, if y1 and y2 satisfy these ODEs, what about z1 and z2? So we'll have a similar system by differentiating both sides of these two equations with respect to t. So we'll have z1 prime equal to um, uh, z2. Now, prime is derivative with respect to x, as I mentioned. We're also differentiating with respect to t, but those differentiation operators commute with one another. So we just get, the first equation is relatively straightforward. We'll just get z2. The second equation is going to be more interesting. So derivative of y2, y2 prime with respect to t is going to be z2 prime. And now we got to take a derivative of this with respect to t. So that's going to be, we need a chain rule for this. Now, x and t are independent variables, so nothing will come from that. What we will have is f df dy times, actually, it would be, yeah, this is df dy. Remember, okay, I'll make a note here. y1 comes from y, and y2 comes from y prime, which again is dy dx. Okay, so for chain rule, I have df dy, dy dt, but that's just going to be z1 plus partial of f with respect to y2, which is y prime. So f y prime x y1 y2 times dy prime dt, but it's the same. That's the same as dy2 dt, which is z2. So now we have the second equation in our system. So what we have to do to apply Newton's method, to apply the shooting method to solve this boundary value problem, by using Newton's method to solve this equation, we have to solve all four of these ODEs. So really we have a system of four ODEs that are coupled together. Notice that y1 and y2 both play a role down here. So we cannot solve these completely independently of each other. Now, these two we can solve by themselves, but solving these depends on these. Um, so then, once we have computed all four of these unknowns, then we can use y1, evaluate it at x equals b up here to get a value of capital F, and then we can evaluate z1 at x equals b um, right here. So I'll just make that explicit. Right, so that's z1 of bt. All right. Now, um, so that's how we can carry out um, Newton's method. Now, one thing we also need initial conditions for z1 and z2. So from initial conditions, where we have y1 of a is equal to alpha from the first boundary condition at x equals a, y2 of a is t, that's our guess of y prime of a. We have to differentiate these initial conditions with respect to t also. So z1 of a will just be 0 because alpha is a constant, and then z2 of a will be equal to 1 because we're differentiating both sides of this equation with respect to t. Okay, so now the initial value problem that's a system of 4 first-order ODEs is completely specified now that we have 4 initial conditions. Okay. All right. So what I will do now, I'm going to refer you to the text, algorithm 13.1.2, and the example on the same page. So that's all I'm going to type here in the notes, but I will pull this up and walk you through it, because it would just take too much time to type out exactly the same thing here. But I wanted to give a little more explanation than the book gives as to where these ODEs come from. Okay, so now we flip over to that, make this a little bigger. Okay. Okay, the recording was interrupted yet again. Thankfully, I'm almost done. Okay, so this is the whole algorithm, a shooting method with Newton's method. So I want to explain the steps that are given here. So we're trying to solve this nonlinear equation, f of t equals 0. So we need an initial guess for a value of t. And the subject of initial guess is taken up in a homework problem. Okay, so once we have an initial guess, we need to set up solving the initial value problem that comes from our boundary value problem. Now you can think of it as time stepping, but we're really stepping in x. So x is playing the role of a time variable. So we need a spacing. We'll use an equal spacing. We're space stepping from A to B, and we want the evaluated solution at n points, capital N points, in the interior. So if we have the interval AB and n interior points, that requires n plus 1 subintervals. So that's why we use this spacing, h, that gives us n interior points. Now, so what we do is the outer loop carries out Newton's method. So K is for iterates of Newton's method. And inside the loop, we will solve this initial value problem of 4 ODEs with the current guess of t that we have, a tk. So we fill in our initial values right here. These are 4 initial conditions. The inner loop here is our solving the IVP. So it's again, space stepping, if you will. That's like time stepping in x. Since we have n plus 1 subintervals, we need to take n plus 1 time steps. So here we're stepping from point xi to point xi plus 1. So here's our current x value, and we're stepping to the next one. So here we're using just Euler's method for time stepping for simplicity. So here we have, this is the time derivative. Whatever's multiplying h is a time derivative. You can just read that right off the 4 ODEs. So we carry out in these 4 lines Euler's method. If you were using a different time stepping method, so like Runge-Kutta, 4-4 Runge-Kutta, for instance, it would only affect the contents of this inner loop right here. Nothing else would change. When you come to the end of this for loop, you've computed the solutions of your 4 unknowns from your initial value problem. So now we need to carry out the Newton's method step, and that is what is done here. Now recall that Newton's method is the following. New value equals old value minus function value divided by derivative. So the function value is your y1 evaluated at x equals b. Well, that would be point of the x value was index n plus 1. So it's the last x value, and it's y1 that represents y of x, and then minus beta. So what's in parentheses here is the f value, so capital F of t, that was computed using this t value. Then we divide by the derivative. The derivative comes from z1, also evaluated at x equals b. So that corresponds to b's values right here. So this is what goes in the numerator, and this is what goes in the denominator. And then we just keep iterating. So each iteration of Newton's method is pretty expensive because it involves solving a whole initial value problem. And that's a process, and hopefully we get convergence to the solution of the original underlying boundary value problem. If you were using a different um, iterative method or different root finding method, such as secant method, you would not need these z's. These are only needed because we need the derivative for Newton's method. So there'd be less work, would not converge as rapidly, but doing less work per iteration of your root finding method may be worth it. Okay. Now, so as an example, here's a sample nonlinear boundary value problem on the interval x goes from 1 to 2, and here are your boundary conditions. Shoot newt is a function that will be part of your homework for the section 13.1. And okay, so what we do is function handles for f and then df dy and df dy prime. So if you take derivatives of this function here that comes from the boundary value problem, so y cubed minus yy prime, that is your f of x, y, y prime. Taking derivatives of that with respect to y and y prime gives you these function handles f and fyp. So now we specify the x values and the y values from the boundary conditions, how many interior points you want to use, and those are parameters to this function. So this does all the actual work. This happens to be the exact solution. Y of x is equal to 1 over x plus 1. And then it goes ahead and plots the solution versus the exact. And those are plotted here, and we see that they agree putting very many points, just 10 interior points. Okay. So this is an example of how the shooting method can be carried out with, but you have some things you can choose. You can choose your time stepping method for solving your initial value problem, and you can choose your root finding method to carry out the iteration. A quick glance at homework problems for this section. So this one deals with how many, how you might choose an initial guess independently of the function f. So a very simple-minded choice, but one that is easy to compute. But suppose you're using the secant method. The secant method, as you remember from chapter 10, requires 2 initial guesses. So after implementing Newton's method in this function, based on the algorithm that was just shown, you can modify that to use the secant method instead, which simplifies a lot of things, but you need a second initial guess. And that one would be based on the particular function f from your ODE. I mean, there's different ways of choosing initial guesses, but so a couple of ideas are explored here. So that's all for the shooting method. So I will spend the next 2 classes, which are the last 2, so one more this week and one more next week, about an entirely different approach to solving boundary value problems, that is finite differences. So later this week, I'll talk about the linear case, and then I'll generalize that to the nonlinear case next week. So until then, and please keep the homework coming. And with each assignment, as I get enough submissions, I'll go ahead and grade it, and then of course I'll have everything graded by the end. Remember, May 14th is when all the work has to be in. Till next time.